Okay, welcome to lecture number 8. Here we're going to start chapter 3 and let's begin our discussion of energy and work and all that kind of stuff. Now, what is energy? Well, energy is a word that we use in everyday life. I have no energy to do this, or, energy, I need the energy to go to the store, to get out of bed, to mow the lawn. All right, energy is a tough thing to define in terms of physics. So we're just going to give a general discussion. For us, energy is going to be something that has energy. We're going to say has the capability of doing work. So I'm going to write this. Energy, and I'm just going to write this. Capability of doing work. Great definition, simple, beautiful, except we've just used a word we really don't know how to define yet. Once again, work. What is work? Well, again, work is doing your homework, mowing the lawn, getting stuff done. But you need energy to do it. Where do I get my energy? My energy came from a bowl of oatmeal I ate this morning. Chemical energy, food energy. All the energy that we have is derivable from the sun. Everything comes from the sun. Now, we know the sun has nuclear energy. We'll learn about that later on. Fission and fusion and ways of producing energy, radiation energy, okay, mechanical energy, chemical energy, lots of forms of energy that we'll talk about. But for now, energy is the capability of doing it. Now, what is work? Work, for us, in words, just very simple, is getting something done. What do I mean by getting something done? All right? Well, getting something done could be a good thing, could be a bad thing. If I throw a ball and break a window, I've done something, but maybe it wasn't too good. Okay? Now watch. Suppose I have my energy, my bowl of oatmeal. Now, consider the fact that I'm going to push on this wall for 1 hour. I'm going to push with all my might. At the end of 1 hour, what happens? I'm probably collapsed on the floor. Why? I've used a great deal of energy. But the question is, have I done any work? The answer is, I haven't done any work. I've used a lot of energy, but I haven't done any work. So we're going to define work in a physics sense. Okay? What symbol should we use for work? Good one. Let's use a W. So here's how we're going to define work. Work is going to be the force applied to an object. I'll go like this. Times distance that object is moved. So now we have the answer to the question of how much work I did by pushing on this wall for 1 hour and using up all my energy from my oatmeal. The answer is zero work. Why zero work? Well, I applied a force, but the wall, the object, did not move. Remember what force is? Let's just review for 1 second, and then we'll talk about work and the units of work. From Newton's second law, okay, let's get rid of this. Okay, there we go. From Newton's second law, if you remember, F total was equal to the mass of the object times its acceleration. Now again, acceleration could be anything. If you're falling up or down, the acceleration or deceleration is g, the acceleration due to gravity, which we took to be 10 meters per second squared. But in general, the acceleration could be anything. Mass, if you'll recall, was measured in kilograms. A was in meters per second squared. And we said this unit of force we called a Newton. Okay? 50 Newton force, 2,000 Newton force. Okay? So now we have work is going to be a force times a distance. So if we look at the units of force, I'm going to write this out, what a Newton is. It's a kilogram, meter per second squared. And what's the units of distance? It's going to be a meter again. So the units of work are kilogram, I'm just going to write m squared per second squared, meters squared per second squared. So this big unit, kilogram meter squared per second squared, is what we're going to measure work in. It's going to be our unit of work. And we're going to give this a name, and this is called a joule. Okay, named after a very famous British scientist. So our unit of work is going to be a joule. So now I could say I did 50 joules of work, 10,000 joules of work, 200,000 joules of work. Just as I can give a quantitative measure of how much force by measuring it in newtons, right? 200 Newton force, 3,000 Newton force, and so forth. Okay? Great. Now, let's do an example. Let me give you a silly little example and see if you can follow. Okay? Suppose I get a summer job. I get a nice gig. I'm working in a warehouse. Okay, my job, once I'm completed, I can go home. Fantastic. Okay, but my job is that I have to move 100 crates from one side of the warehouse to the other side of the warehouse. When I complete that, I can go home. Great. Little old man, no muscles. What can I tell you? So here I go. Start my job at 9. Go over, get a crate. Walking. All right, walking. I need to rest for a while. Okay. And then I go get the next crate. By 5, 6 o'clock, I'm done with my job. I'm exhausted. They pay me, and I go home, and it's great. Now, there's a young stud working here, Igor. Igor's got many muscles, Igor. Igor, same job. He's got to move 100 crates from one side of the room to the other side of the room, the warehouse. Okay? Igor's muscle. So Igor takes about 4 boxes at a time, one hand. He's on his phone, texting his lover, and next thing you know, he puts them there, goes back, not even winded, right? Igor starts the job at 9, just like me. By noon, he's done with the job, he goes home. Now the question is, who did more work? Igor, the muscles, or the old man with no muscles, 1 box at a time? Well, the answer is we both did the same amount of work. We both moved 100 crates from one side of the warehouse to the other side of the warehouse. However, if I ask the question, who's more powerful, Igor or me? The answer is obviously Igor, because Igor took much less time to do the same amount of work. So we're going to define something called power. We would say he's more powerful. Okay? Power, symbol P, good, right, is going to be amount of work done divided by the time it takes to do the work. Okay? So power is going to be work over time. And we said the units of work were joules. Unit of time is going to be a second. And so our unit of power, is going to be a joule per second. We'll give this unit a name. What is the name? Can you tell me? What is the name? What is joule per second? Very good. It's a watt. This is defined to be a watt. What's a kilowatt? What's a kilowatt? Well, it's 1,000 watts. When I leave a room and turn out the light, I kilowatt. Kilowatt. See? Kilowatt. Silly. Okay, so our unit of power is going to be joules per second is watts. Okay, so let's go back to energy. Remember, if you have energy, you can then do work. Many types of energy: energy of motion, energy of radiation, nuclear energy, electric energy, mechanical energy, chemical energy, which is food energy, etc. Okay? So let's talk about one type of energy. All right? This is going to be energy of motion. If you put an E there, you get emotion, and the energy of emotion probably is love, but that's for a different course. Okay? We'll stick with physics. Energy of motion. The Greek word for motion is kinesis. If I'm spelling it correctly, kinesis. Kinesis essentially means motion. So the energy of motion is going to be kinetic energy. Okay? Now remember, if you have energy, you can do work. So let's talk about the energy of motion for a second. How much work you can do. Suppose I take a ping pong ball and I throw it at a window. Nothing happens. Suppose I throw it at 5 miles per hour. Nothing happens. If, however, instead of a ping pong ball, I take a brick, a lead brick, and I throw it at the window breaks. So what's the difference between a ping pong ball moving at 5 miles per hour or a lead brick moving at 5 miles an hour? The answer is the mass. Clearly, if something is moving, the greater the mass, the more energy or more damage it's doing. If a child runs into your leg on their tricycle at 2 miles an hour, it's a lot different than a Mack truck moving at 2 miles per hour hitting you in your leg. So we're going to write this kinetic energy, Ke, okay, is going to depend on mass. I'm going to put an M there. The greater the mass, the greater kinetic energy of the object. Now, since it's energy of motion, what tells you if you're moving? If you're not moving, what is your kinetic energy? 0. Okay, so you have 0 kinetic energy if you're not moving. So clearly, this must depend on your speed. All right? All right? The expression, however, without derivation is this. And I want to talk about this. 1/2 mv squared, v squared, the speed squared. Before we discuss this and use this and play with this, let's look at the units, okay? What's the units of mass? Do you remember? It's kilograms. Do you remember the units of V is meters per second? So if we square that, we get meters squared per second squared. So this is our unit of kinetic energy. If you go back a couple minutes, you'll see that kilogram meters squared per second squared was also our unit of work, and we said this was a joule. So work and energy are going to be measured in joules. Well, that kind of makes sense that they have the same units. Remember, the more energy you have, the more work you can do, right? So it makes kind of a bit of sense that they share the same units. Now, this factor of 1/2 is part of the definition. Okay? Listen to me. mv squared is not kinetic energy. It's actually twice the kinetic energy. 1/2 mv squared is the kinetic energy. So, quick problem. What is the Ke, kinetic energy, of a 500-gram object moving at a speed of 4 meters per second. Okay, what is the kinetic energy of a 500-gram object moving at a speed of 4 meters per second? Now I want you to look at the definition of kinetic energy. 1 half mv squared. M is in what? Kilograms. Kilograms, not grams. Meters squared per second squared. So kinetic energy of this object is 1 half mv squared is equal to 1 half 500 grams. We need to convert that to kilograms. What's a kilogram? 1,000 grams. So 500 grams is half of a kilo, right? So we would put here 1 half or 0.5 kilograms. That's the mass. V was what? V was 4 meters per second, and we have to square that. So when we square 4, we get 16. Half of 16 is 8, and half of that is 4. So the answer to this problem would be 4 joules. If you use the mass of 500 grams, you would get the wrong answer. You must convert grams to kilograms. Okay? Now, let me show you the types of problems that I would ask on my exam. So again, I'm going to write kinetic energy is 1 half mv squared. Let's save this right here. Right? And here's a question I'll ask. What happens to the kinetic energy if the speed of an object is doubled? Okay? What happens to the kinetic energy if you double the speed? Well, choice A on an exam would be you double the kinetic energy. And guess what, everybody? Choice A would not be correct. All right? So, what do we do? Well, watch this. I'm going to write kinetic energy is equal to 1 half mv squared. Board sure gets dirty quick, doesn't it? Okay, so this is 1 half the mass. Now, what am I doing to the speed? I'm doubling the speed. So that means v becomes 2v, and now I have to square it. Does everybody understand? I've doubled the speed, but now you square the new speed. 2 squared, you can use a calculator. This is equal to 4 times 1 half mv squared. Now, here's where many students make mistakes. Don't get fooled. Remember, I want to know what happens to the kinetic energy. How much does it change? 1 half mv squared is the kinetic energy. So it's clear that the answer is the kinetic energy increases, in this problem, by 4 times. 4 times 1 half mv squared. Listen to me, pay attention. Look, if you multiply 4 times a half, here's what you would get. You'd get 4 times 1 half mv squared. That's equal to what? That's 4 over, is 2 mv squared. Does everybody see this? 2 mv squared. mv squared is not kinetic energy. 1 half mv squared is kinetic energy. So if you put 2 as your answer, you would be wrong. You cannot put 2. You must keep the 1 half as part of the definition. Do not multiply 4 times 1 half. It's 4 times 1 half mv squared. So this is kinetic energy. So it's increased 4 times. Be very careful. Okay, I will watch the board, and in the next lecture, we'll discuss potential energy, okay? Gravitational potential energy.